pre-tiled small board, when you add pieces to it in some prescribed fashion, it'll result in a large tiled board, but how do I know that every large tiled board can be divided this way? Do you see the distinction? You should start, the assumption is the small board can be tiled, but you should start with the large board and work from there, okay? This may seem pretty obvious in this example, but on your homework, there's a problem where people often mess up the construction by making this error, okay? So the homework, I think, asks you to show that every finite set of real numbers contains its supremum. So every finite set of numbers contains its supremum. Let's just get a hint at how you might prove that. Okay, so you have a finite set of numbers. That seems to be a very general statement, right? A statement about a bunch of numbers. In fact, a finite number of them. So that's a bunch of statements you're trying to prove, right? So you might think, oh, I could prove this by induction. So what should I induct on? How about the number of things in the set? Good, let's induct it. Let's call that n. So I assume you'll do the base case. But now if you're trying to do the inductive step, what should you start with? A set with how many elements? Or k plus 1, right? And then find the k element set within that. Now, the mistake people make every single year when I assign this problem is they'll start with the k element set and add one element to it. Some of you are thinking, well, I don't see the difference. Well, there's a philosophical, I guess, difference in that you aren't necessarily sure that if you don't start with a k plus 1 element set and find a k element set in it, it's not the same thing to say that you start with a k element set, you add one thing, that's general enough, although it happens to be. Okay? Okay, so just be careful of that error. Okay, any questions so far about the principle by induction? Okay, let's take a couple of minute break, and after the break I want to show you some more features of induction, also some other common errors of induction. All right? Yeah.
I have a question about the principle of induction.
Yeah.
Making it a subset of n, wouldn't that make it also a property? Isn't that a property of S also? That it's a subset of n?
It was I'm not sure what your question is. We're assuming S is a subset of n.
But wouldn't that also count as, I guess, I don't know. I feel like that's also a property of S that we're just not saying it's a property.
That what's a property?
That S is a subset of n.
Yeah, this is any subset of n. In other words, you give me any subset you like. This is a statement about subsets of n.
But here's my question. Couldn't we generalize this to make it true for any set S that has those two properties? Why do we need to restrict it to just...
Oh, because we haven't talked about this yet, but it deals with the issue of countability.
Okay. Okay.
So later on, we'll see that you could do this for other subsets of other things.
Okay.
But you need something stronger, which is not logically equivalent to induction. Okay. It's called the principle of transfinite induction.
Okay.
Yeah.
Okay. Also, the principle of
Yeah.
strong induction versus the principle of induction, they don't imply each other, do they?
They are. They do.
Okay.
Clearly, strong induction implies induction.
Oh,
and then the other way you can show by bootstrapping.
Okay.
By induction.
Okay. All right.
Yeah.
Okay, thank you.
Okay, let's resume. Let's do a few more proofs by induction. So here's a theorem, which many of you have seen before. But let's prove it. Prove that if I take the following sum, which I'll call S sub n, and it's the sum of the first several odd numbers up through 2n minus 1, prove that this is a perfect square. So let's just start naively and see where we can go with this. This is a statement that's clearly indexed by the natural numbers. So I immediately think induction, right? And the beauty is I don't need to have insight. Okay? Now, if you had insight, you could certainly do this a different way. But, I might start like this. In fact, I might just call this a scratch proof because we're not sure this is going to work, but let's just see. Okay? Here we go. For the base case, is it true? The base case is n equals 1. Is this true? Base case holds since what? S1 equals 1 is 1 squared as desired. A square is desired. Is this a sentence? Yes. Base case holds since blah. Yeah. Okay. Period. Okay, great. That wasn't so bad. Inductive step. For the inductive step, well, we can assume Sn is a square. If it's a square, I can write it as a natural number squared, right? So what square is it? Maybe, let's say k squared for some k. Right? Agreed? Yes? It's some square. Okay, so what should I start with now if I want to show the inductive step? I want to start with S sub n plus 1. Yes, I guess I'm inducting on n. So we want to show, you might as well tell the reader, we wish to show Sn plus 1 is a square. Okay, well, let's just write it out. Here we go. Sn plus 1 is, now, it would sure be nice if I use the inductive hypothesis somewhere. Sn plus 1 is the sum of the first bunch of natural, of odd integers. And you'll notice it goes up through 2n plus 1. And the term right before it is 2n minus 1, isn't it? So do you see the inductive hypothesis here somewhere? Really? Where? Ah, right here. So this is S sub n plus 2n plus 1, which is, S sub n is a square. This is k squared plus 2n plus 1, which, not so helpful. Gosh darn it. I sure was hoping that this inductive hypothesis was going to help me. It doesn't look like it